So, reading a basic article on my forehead, quantum entanglement. I was resting my head on a chair. Looks like I have a battle scar. Oh, jeez. So, I'm not gonna stop laughing at that. Entanglement is the idea that two separate particles can exhibit the same quantum effect or state or whatever. Honestly, I've never even found a fucking experiment demonstrating it at all. I've looked for years. So, I just have to go at it with my own brain. And I have various explanations for what has been described and how I would, explain these phenomena. But this article actually explained one experiment in that once they could change the angle of the measurement, the other particle exhibit a new state of superposition and its spin could change. And so, to me, that means that there kind of is no such thing as quantum entanglement, as I suspected. That there's a probability of two particles exiting a crystal that encounter a very consistent quantum state within the crystal that really only limits the effect upon the particle to, and there's a higher probability that when they exit they will be in the same quantum state, which means that they're not actually entangled, they're not touching each other as they travel through space, because there's no study that I've found to explain. And from what I've heard is if you interact with it, you break the entanglement. But supposedly then that transmits some sort of broken quantum state to the other particle. Well, we don't have any constant measurement. I mean, if you send out the entangled particles, you would need like a series of entangled particles in a line, right, traveling back, and then to measure them all as they all travel, and then change the angle as they all travel to see how this side and its constant of measurement versus this side as it changes the angle of measurement, how the string of entangled particles one by one change and evolve. I suspect that the best way that I can imagine it, aside from getting into other field theory that I don't even know the words for, that I have conceptualized how it could work, but I believe that this is the actual answer, is that it's like two balls that you're dropping in water, and if you push on this one, that sends a wave, and this one starts moving. Well, what if you start pushing on them independently? And that's similar like spin up, spin down. Let's say pushing down is spin down. And so the waves, as they pass back and forth to one another, as you know, are going to start like evening out and things, right? So they're going to impact upon one another, the crests and troughs. And if you have a frequency of doing it, then the spin up and spin down. See, I don't know if like the data for when they even do the measurements. How do you like I said, there's no constant measurement. They're not conveying, or whether or not like this one's spinning like 2 times and this one's just 1, and then we happen to measure it when they both equalize at the waves pass through one another, and right when they're measured they can be flat or they could be opposite. If that makes any sense. It makes sense in my brain, but that's the best, like, I don't know if that's a metaphor or analogy or whatever it is. Thought experiment. There you go. I just woke up. I'm really tired. Just exhausted. So, going back to how it would be really interesting then, because we know that at the quantum level of chromodynamics, the wave functions do create interference patterns, right? So there's possible that there's a probabilistic field of chromodynamic effect that's impacting on these particles. And so when you have them sent back and forth to one another, then, so let's say we create like a triangular structure here, or like a rhombus. If we could make a rhombus that could form into a square and back, and then, you know, these two detectors come closer together so that as these particles are being shot back and forth to one another, that then we could do this, and then we could change the shape of how the detectors are imparting and packing and detecting as these particles pass through one another, sort of thing. And if two entangled particles, then I hope I'm making sense, as they impact and impart their wave functions on one another, what would happen after those particles then are detected? So you'd shoot two entangled particles, and then, you know, two entangled particles to entangle at the same time, and then you would take what is an even effect, perceptibly even, where everything would be at like 90 degrees. Then you change the degrees to which, if they can do that, I don't know. I'm not in a, I don't work in a lab, so I don't really know a whole lot about entanglement other than what I've interpreted all these years and tried to figure it out. From my understanding, I think that they can change the angle at which they depart from one another. They're not traveling parallel to one another. They can travel at a great angle and travel indefinitely. So that means there's no resistance. Well, like a swimming pool, though, those waves meet viscosity and gravity. But if they went on forever, because there was a superfluid, well, even though fluids have zero viscosity, so when you look at it like that and you call it like a, you know, like space, it's pretty funny. Where could the wave come from? And how could then these, I don't know, would it be quantum vortices or vortexes that are created that could correlate down to, like I said, quantum chromodynamic effect, where like the wave functions then spin. If you had to, like, imagine it like in the superfluid, and you have that, what do they call that in superfluid when the vortexes form, then that would be linked all the way across. Oh, physics is fun. Hey, my red spot kind of went away. Oh, so silly.